Hello viewers, welcome you all. Today in this lecture, I am going to taking up the next topic of high energy physics or particle physics, and the topic is the question based on a Quark model, right? Quark model. Right? Uh, I have discussed Quark model in detail in a separate lecture. So if you want to go in details about the Quark model, then you can click on that video lecture and go to all the details. In this lecture, I am taking some questions that can be asked from Quark model, and different properties of the elementary particles on the basis of a Quark model, right? So we know very well that Quark model was developed in 1960, particularly 1964, by two physicists. One was Murray Gell-Mann, right, and the second was George Wigg, right. So according to that model, Quark model, all the hadrons means mesons and baryons, right? They are made up of some more fundamental particles, and these particles will called as quarks, right? So we know very well that quarks comes in 6 different flavors: up, down, strange, sorry, charm, top, and bottom, right? So these are different quarks, and I have arranged them in accordance with their mass. So now I'm coming to the questions, right? These are the 6 quarks: up, down, charm, strange, top, bottom. We know very well that they contain electric charge. This is having charge plus 2 by 3e, minus 1 by 3e, right? Then strange again minus 1 by 3e, this plus 2 by 3e. Then this bottom top has plus 2 by 3e, and this bottom minus 1 by 3e. All these things has been discussed in that lecture. We know very well that what is the mass of these different quarks, and mass is expressed in terms of energy. So question can be asked that which of the these quarks, 6 quarks, is the heaviest one. So if we look at the mass of these different quarks in terms of energy, then we know that the mass of top quark is around 20 giga electron volt, right? And of bottom, it is 5 giga electron volt. Similarly, these up, down, and strange, these are the lightest. Lightest means they have a light mass. The mass of this one is 330 mega electron volt. Down is around again 330 mega electron volt. Then strange around 500 mega electron volt. Charm, right? Charm is 1.5 giga electron volt. So you can see as we are moving down, the mass is increasing. So the question can be asked from the mass that which of the these 6 quarks is the heaviest one. So obviously the heaviest one is this, right? And here I have expressed the mass in terms of energy by taking C is equal to 1, H cut is equal to C is equal to 1, right? You can you can see here divided by C square. So don't bother about the C square, because in this table I have taken C is equal to 1, right? So we know that these different quarks have different quantum properties like strangeness, charmness, right? Then bottomness and topness. Strangeness quantum number is -1 for strange quarks. For the other, it is 0, 0, 0, then 0, 0, 0, right? Similarly, charmness quantum number is +1 for the charm quark, right? And it is 0 for other. Similarly, the bottomness is 1 for only bottom, +1 for bottom. Topness is 1 for only top, right? So these are the different properties, important properties of these different quarks. As far as spin is concerned, we know that all these quarks has a half integral spin, right? 1 by 2 h cut, or simply we can say 1 by 2, right? As all these quarks are having half integral spin, so they are basically fermions, right? As far as the virion number is concerned, it is B is equal to plus 1 by 3 for all these quarks. Remember that when we are talking about the anti-quarks, anti-particle of these quarks, then these properties will get inverted. Inverted means the sign will get changed. I mean, in that case, if I'm talking about the anti-up quark, then that will have virion number minus 1 by 3, right? Similarly, spin will get inverted. Similarly, strangeness will get a plus 1, right? If I talk about the anti-strange quark, right, the strangeness will become plus 1. Similarly, charmness, bottomness and topness. So all these properties will get inverted for anti-quarks, but the mass will remain same, right? Similarly, charge will also get inverted, right? As I told you that the up has charge plus 2 by 3e, right? Anti-up quark will have it will be minus 2 by 3e, right? So these are some property that I am recalling here in order to proceed further. So question can be asked from this table, and it is very important that the question may be asked from the mass of these different quarks, right? Which of these quarks is the heaviest one? Which is the lightest one, right? Or which of these quarks have strangeness quantum number minus 1, right? It can be asked from their spin, right? So then after I am proceeding further, then after it comes, as we know that quark constitutes mesons and baryons. So we know very well from the knowledge of quark model that meson consists of a quark and anti-quark pair, whereas a baryon consists of 3 quarks, right? This is again we have to remember, right? Now the one more thing that we know that the quark have some special quantum property that we call color charge, right? We have also keep it in the mind that in meson these 2 quarks, one is of color, then the second is of anti-color. So the meson is always colorless, right? Similarly, in baryons, the 3 quarks are in of different colors, and they again make a baryon colorless, right? So in both the situations, the resultant configuration that we get after combining either 2 quarks or 3 quarks, we get a colorless combination. All these things has been discussed in the Quark model. That's why I am saying that you can refer to that lecture also, right? Now I am coming to the important part that is usually asked in the examination, that is the quark content of different elementary particles, right? So we know very well that from this knowledge that meson consists of quark and anti-quark, whereas baryon consists of 3 quarks. So we have to memorize that table, that what is the combination. So if I come to the combination, then I'm starting from proton, neutron, simplest one, right? Then proton, as far as proton is concerned, proton, neutron, sigma, right, naught, sigma plus, sigma negative, then lambda naught, right? All these particles, right? Proton, we know it is up, up, down, then down, down, up, quarks. Sigma naught is up, down, strange. Sigma plus is up, up, strange. Sigma negative is it is down, down, strange. Then lambda naught is up, down, strange. So in this way, you have to memorize all the elementary particles quark content. The important one that I usually ask is like omega negative. Omega negative has a 3 strange quarks, strange, 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 right? And this was the particle that was responsible for assigning color charge property to the quark, because otherwise all the 3 quarks are same, but they comes in different flavors, right? They have different color charge, these 3 strange quarks. That's why it makes it colorless, right? So the question can be asked from here also, right? Similarly, there are some important, elementary particles. From they are usually asked like delta negative, right? Delta naught, right? Delta positive, right? So the quark content of these particles are d d d, down down down. Oh, sorry. Yes, down down down. Then here delta naught is up down down. Delta plus is up up down, right? Similarly, delta positive, then delta double positive. It usually asked in the exam, up, 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 right? Then one more particle is there, that is pi naught. Pi naught is usually taken as a 1 by root 2, right? Its quark content into up, up naught plus down, down naught, right? This is about the some important elementary particles and their corresponding quark content, right? Now, if you are suppose given a particle and you are asked to write down the quark content of that particle, or suppose you are given a particle and a quark content of a particle and you are asked to identify that particle, right? So in that case, the best way is how you can check that which of the particle is you can simply add up the different quantum properties of these quarks, right? And then after whatever properties like baryon number, spin, charge, right, strangeness, according to that you can decide that which particle is this, right? Here I think I have mistaken, it is negative, up up naught minus down down naught. In case of pi naught, it is usually asked up up naught, down down naught, right? So I have listed some important elementary particles and their corresponding quark content, right? And as I told you that by taking into account the quantum properties of these different quarks, I have written all these properties here, I can check that which is the given particle is in terms of its quark content, right? By simply adding up the quantum properties of the combination of quarks, right? Now, one more question that is usually asked from this quark model, or I can say from the elementary particle, it is their Bake diagrams, right? Or symmetry, right? Symmetry properties of elementary particles. So I'm not going into all details of that, but we know that when we go into the SU2, special unitary groups in 2 dimensions or specially unitary groups in 3 dimensions of these elementary particles, then when we write down the Bake diagrams, right? Bake diagrams, right? Then it is found that these elementary particle can be classified into different groups, right? That groups make the predictions of the unknown particles just as we make the predictions of unknown elements in the periodic table, right? So these weight diagrams are very important and we have to memorize it, because question is usually asked from the weight diagram. So I am drawing here weight diagrams are simply, I am not going into all details, they are simply diagrams that are made by taking the consideration hypercharge and the Z component or I3 of iso spin. So we have a hadron, we are talking about the hadrons, right? Hadrons means mesons and baryons. So if I talk about the mesons, then in meson family I can have 2 type of mesons. One mesons are those for which JP stands for angular momentum, I mean spin and parity. So one group is that for which JP is 0, angular momentum or spin is 0 and parity is negative, right? We call them as pseudoscalar mesons. Right, but we have other mesons also for which the spin is 1, right, and again parity is negative. These are called negative. These are called vector mesons, right? Mesons are basically, we know very well, they are bosons. They have either zero or integral spin. So if I talk about particularly about this, pseudoscalar mesons, then when we arrange these pseudoscalar mesons in terms of their hypercharge and isospin, then we got a non-net or a octet, right? I am showing you here. This is the one axis, and this is other axis. One axis is representing the hypercharge, and other is representing the isotopic spin, z component of isotopic spin, right? So this is I3 and this is a hypercharge. So if I arrange, as I told you, that these pseudoscalar mesons in this graph, then it is found that this one, right? So sorry, this one. So when I place these elementary particles, pseudoscalar mesons in this graph, and the graph is plotted between the taking into consideration hypercharge of the elementary particle and z component of isospin, then it is a z component here, it is 0, it is plus 1, it is minus 1, right? Similarly, if I talk about the hypercharge, it is 0, it is plus 1, right, and it is a minus 1, right? So when we plot a graph, we got this type of graph. You can see now the resultant shape. This is called pseudoscalar. Here at the origin 0, we have a pi naught, right, eta and eta dash meson. 3 meson at the center. This is k naught, this is k positive, this is k negative, and this is k naught antiparticle. And here it is pi positive, here it is pi negative. So 1, 2, 3, 4, 5, 6, 7, 8, 9 mesons are there. So that's why it is called a pseudoscalar non-net of mesons, right? So as I was saying that question can be asked that which of the these particles is this, right? If I talk about the I have plotted two properties. This is minus 1 plus 1. Here it is I forgot to tell you, minus 1 by 2, it is plus 1 by 2, right? Similarly, here it is minus 1 by 2, obviously on this axis, and here it is same thing, right? It is minus 1 by 2, it is plus 1 by 2, right? Here it is plus 1. We are taking into consideration the I3, z component of isospin along this axis and hypercharge along y-axis. So hypercharge at the center is 0, as I told you. Here it is plus 1 and here it is minus 1. Here isospin at the center is 0. Here it is plus 1 by 2, right? And it is minus 1 by 2, it is minus 1, and it is a plus 1, right? So this is now I was saying that we have to memorize this non-net of mesons. Question can be asked that which of the particle is at the center of the pseudoscalar non-net of the mesons, right? Or which is at this position. Examiner can ask any question, right, based on this diagram. This is called non-net, right? This is the Bate diagram that I talk about in the beginning. Now this is about the pseudoscalar mesons, non-net. If I remove this eta dash meson from here and I consider only 8, then this is called a octet, right? Then we call it as a pseudo scalar octet, because in that case it will become octet, 8 particles, right? So all the things will remain same, only one thing is different, that is we are removing this particle from here, right? Now I am coming to the next is about the baryons, right? So in baryons we have two type of baryons. One, we know very well, baryons are fermions, right? So obviously their spin is either plus 1, either 1 by 2 h cut or 3 by 2 h cut, and according to that they can have different parity, right? So we have two groups. One is for which Jp is equal to 1 by 2 and positive, right? This is one group. Other group is for which Jp is 3 by 2 positive, right? So 1 by 2 positive group forms octet, right? Octet, and this group form a decuplet, right? Octet and a decuplet. Right? So this is about the baryon groups. Now I can classify the baryons according to that. So again I have to draw a weight diagram, right? So as far as weight diagram is concerned, again for the octet I will get similar kind of diagram as it is shown here, right? I am erasing all these from here particles. The other things remain the same. I mean, we are plotting the graph between the hypercharge and third component of isospin, right? Here the center it is 0, it is -1, right? And it is on this axis it is -1, as I have written here, it is +1, right? I have written here, and it is -1 plus 1 plus -1 by 2 plus 1 by 2. So in this case we get neutron here, proton here, right? Then here it is a sigma positive, here it is a sigma negative, here I got a xi negative, here I got a xi naught, right? And at the center I got a sigma naught and lambda naught. So again you can see 1, 2, 3, 4, 5, 6, 7, 8. 8 baryons have been assigned different positions in this weight diagram. So obviously it is a octet. You can see octet of baryons with Jp is equal to spin and parity is equal to 1 by 2 positive. Positive means they have even parity. Now again we have to remember this diagram, that which particle is present at the bit position, right? Now I am coming to the second one. The second one is about the decuplet, right? So for decuplet, right? So this is again hypercharge by, right? This is I3, right? It is 0 here. It is, we are taking plus 1 by 2, then we are taking 1, then we are taking 3 by 2, right? So it is 1, 2, 1 by 2 minus 1, 2, it is minus 1, 1, 2, it is a minus 3 by 2, right? Again here I have this is minus 2, this is minus 1, this is 0, this is plus 1, and yes, right, minus 2, minus 1, 0, plus 1, and this is plus 2, right? So now I am going to place the different particles here. First of all, let's make the decuplet. This one, this one, and this one. This is the diagram, right? Now I am putting up different particles at different positions. So here, first position, then second one, then third one, fourth one, fifth, sixth, seventh. In place of 0, I will have minus 1 here and here, minus 1, 2 particles at this position and this position, and minus 2 this position, right? Here it is omega negative, right? Here I have 2 particles, xi negative and psi naught. Here I have 3 particles, sigma negative, sigma naught, sigma positive. Here I have delta naught, and here it is a delta positive. Then here we have a delta double positive. Here we have a delta negative, right? So now you can see here 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you can see here now all these 10 baryons has been placed on different positions in this weight diagram, and it is called Jp is equal to 3 by 2 plus decuplet of baryons, right? So once again we have to remember all the positions, right? Usually question can be asked that, but which particle is present at this position, right? That is hypercharge is equal to minus 2, and z component of isospin is equal to 0. So you can tell that which particle is this. Similarly, all other positions of the particle, you should know all these positions, right? That which particle is present at which position, right? So this is very important. These 3 weight diagrams. This is decuplet of baryons. This is pseudoscalar nonet, not nonet, but it is octet of baryons. I have erased that third diagram, right? Similarly, it was a pseudoscalar nonet of mesons that I have erased. So we have to remember all these 3 weight diagrams because question can be asked from here, right? So usually in a quark model, the question are asked either from the quantum property of different quarks, quark composition of different elementary particle, I told you, right, of some important elementary particles. Then the weight diagrams, the diagrams that arise from the symmetrical arrangement of different elementary particles that comes from SU2 and SU3 symmetry. Although it is a very big topic. If you want to go in all details, you can go to my Telegram channel. There you can find the different notes regarding SU2 and SU3 symmetry and how these weight diagram arise from there. But here I am only drawing this diagram to memorize these diagrams, right? So this is all about the this quark model. Now I am taking up some questions, right? I am referring to some question papers of some competitive exams, and I will try to solve the problems of those exams by taking into consideration all these knowledge that I have gained from this discussion, right? Now you can see here on the 65th question, you can see here the question is the experimental evidence. Let me make it larger, right? The experimental evidence that support the existence of color quantum number of quarks. I told you in the beginning that the color quantum number was assigned because of omega negative, right? Although this is also responsible delta double positive, you can see here delta double positive, right? Up, right? Three quarks, same quarks exist in this quark. So how it is possible? Because they are violating the Pauli's exclusion principle. So it is not possible for them, right? Same kind of thing is happening here, right? So obviously the answer is that these two particles are responsible for assigning of a color charge to the quarks, right? So the answer is this one, right? I'm coming to the next question. You can see here a Baryon octet with quark substructure down strange has an isospin, strangeness and hypercharge. Quantum numbers are given by a Baryon octet with quark substructure down strange. Now once again down strange, right? Down strange, right? This one, right? Sigma negative, right? Sigma negative down strange. Now look at the weight diagram. Sigma negative, this one, right? I3 -1 hypercharge 0, right? You can see isospin strangeness. The particle was sigma negative, right? And Baryon octet, right? With quark content. This hypercharge was, I forget, sigma negative, hypercharge was 0 and it is -1. Hypercharge is 0. So y is equal to 0 here. Only in this option hypercharge is equal to 0, right? You can see here isospin is equal to 1. Obviously for this group the total isospin is 1, right? Because 2i plus 1 is equal to 3. So I is equal to 1, right? And for particularly for this sigma negative, the z component of isospin was -1, right? But here the examiner has asked you about the isospin I. Strangeness, right? It is obviously -1. We know very well. But the thing that decides the answer is this, y is equal to 0. So this is the correct answer, right? Now, baryon number V, charge C and isospin of a quark are respectively. We know very well baryon number is a +1/3 for a quarks, right? Charge can be +2/3 E or -1/3 E. The examiner is talking about the quark, not anti-quark, right? So charge +2/3 and isospin, right? Charge plus 2/3, right? Here it is given because for quark this baryon number cannot be negative. So this option is deleted. This option is deleted, right? And here for quark charge cannot be -2/3e because he is talking about the quark. For quark it is +2/3. So the correct answer is this, because again it is deleted. So this is the way of deciding the answer, right? So this is about this question. Now the next question is, out of the following elementary particle, identify which are the fermions. Now fermions, pi positive, boson, mu fermion, neutrino fermion, this fermion, this. So except this one, pi positive, right? Or no, sorry, K meson is also a boson. So this one, this one, this one, 3. So here look at the options: mu negative, neutrino associated with electron, and sigma particle, right? This is the correct answer, because pi meson, this option is deleted, this option is deleted, this is deleted. They are bosons. So the correct answer is this, right? So these were some questions from this paper that I discussed with you. Now I am coming to another paper. You can see here. Now you look at this question: which of the following process is allowed? Right. So as far as the nature of the process, whether it is allowed or forbidden, we have to apply all the rules, right? Like virion number, lepton number, all the conservation laws. Then only we can tell that whether the reaction is allowed or forbidden, right? So by applying virion number, right? Baryon number, lepton number, isospin, Iz, right? Then strangeness, right? And hypercharge. Conservation laws, I can tell that which of the following reactions is allowed, right? You can initially check by applying the lepton number and baryon number, right? So if these are concerned, for example, here baryon number, right? 0, 1, 0 plus 1, right? Conserved. Lepton number, conserved, right? Then we have to come to isospin, right? Isospin is for this isospin pi negative, it is 1, right? For proton group, it is 1 by 2. So for K negative group, for this isospin is 2 members in the group, 1 by 2, right? It is for sigma, it is 1. So isospin is also conserved, right? Now look at the strangeness, very important. So here these two particles are not strange. K mesons and this sigma particles are strange. So we have to look at the strangeness quantum number of K negative and sigma positive, right? So if I look at these two quantum numbers of K negative and this particle, then they are K negative and you can see here. So for K negative, strangeness is -1, right? It is -1, and for sigma positive, it is again -1, right? K negative -1 and it is K negative, yes, K negative -1 and sigma positive, it is a -1. So it means strangeness quantum number is not conserved here, right? So strangeness quantum number is not conserved, means this is not allowed. So this is decided that it is not allowed. Similarly, you can check others by applying these conservation laws. You can now apply I3 conservation law also here. Then it will be decided, but it is already decided that this is not allowed, right? Similarly, you can go to this one and this one, and you can decide, right? Now this question, actually I have solved some problems in yesterday's lecture, so you can solve it, right? Now I am coming to this one: quark content of K negative mesons, right? K negative. Now for that, if I have written here K negative, no, I have not written here K negative, right? So for K negative, again I have to look at the table, right? K negative, it is a strange up knot. Strange up knot. This one, K negative. Strange up knot is the quark content of a K negative meson, right? Now, this question again, a virion belonging to SU3 octet consists of the three quarks, right? He is talking about the SU3 octet, right? And virion octet. Down, strange. Again, same thing, it has quantum numbers, isotopic spin, right? And strangeness and hypercharge. So, down, strange. I think we are getting the same question, down, strange. So, down, strange is, I think it was a sigma negative, down, strange. Down is down, strange. So yes, not sigma negative, but it is a xi negative. Down, strange, right? In that question, what was there? Let me check it. It was down, strange, right? In that question, it was a down, strange, right? So down, strange was a sigma negative, right? But here in this question, it is, the examiner has asked down, strange. So as I told you that down, strange is xi negative. Now we have to look at the virion octet. Xi negative is at which position? This one. So hypercharge is -1 and I3 is also -1 by 2. -1 by 2. It is hypercharge is -1 and I3 is -1 by 2. So isotopic spin -1 by 2 is also given in this, and hypercharge is -1 also given here, right? But let's consider other options. Isotopic spin 1 by 2 deleted, 1 by 2 deleted, 1 by accepted, but hypercharge is +1. So all these options are rejected. This one, and this one. So the correct answer is this, right? And strangeness, we know very well that strangeness of xi negative is -2, right? We know very well that strangeness is negative, right? Hypercharge is -1 and isotopic spin is -1 by 2. You can go to it. You can check here again, right? So these are the questions that are asked from these weight diagrams, right? Now, if you don't remember, suppose weight diagrams, even then you can find out these properties by taking into the consideration of these down, strange, then joining all these quantum properties, and then after making this, right? This is about this question, right? So now I am taking the next question. You can see here the next questions are question number 98. Consider the reaction omega negative xi naught plus pi negative. Which of the following statement is false? Charge is conserved. Look at the reaction. Yes, it is conserved. Baryon number is conserved. +1 conserved. Strangeness is conserved. -3, -2, 0 not conserved. Parity is conserved, right? So the correct answer is this. This statement is false. Strangeness is not conserved, right? Then the next question is, which of the following is not conserved for electromagnetic interaction among elementary particles? Isospin, let's start from the isospin. Del I is equal to 0 for a strong, right? Interaction, and del I not equal to 0 for a electromagnetic and a weak, right, interactions, whereas del I3 is equal to 0 for a strong and a electromagnetic. It means third component of the isospin is conserved, right? Strangeness, right? Which of the not conserved, right? Strangeness, is also conserved in the electromagnetic interaction, right? Parity is also conserved, or it can be non-conserved, but we usually take parity is conserved in electromagnetic interaction. There is rare violation, right? But isospin, right, it is equal to 0 for strong interaction, non-equal to 0 for electromagnetic and weak interaction. So this is the correct answer, right? So we can decide it. In earlier lecture I have explained all these conservation laws. So isospin is not conserved. Now next question is the quark content of delta positive. Now refer to that diagram, delta positive, and here I have delta positive, up up down, right? You can see, so up up down, C is the correct answer. So as I told you that these are some important elementary particles which are usually asked in the examination, and these weight diagrams. So these were some questions from the quark model and elementary particle that I have tried to solve in this lecture. If you have any question based on these problems, these topics, then you can share it with me, then I will try to solve that. And I think these are the topics that can be easily done in the competitive exams if you have knowledge about all these things, right? So this is all about it. Thank you very much.